Let's solve a problem about stopping distances for an automobile. A car is traveling at 95 kilometers per hour, and the driver has a reaction time of 1.0 seconds. We need to find the total stopping distance in two cases. First, when the car decelerates at 5.0 meters per second squared, and second, when it decelerates at 7.0 meters per second squared. Before we start calculating, let's understand what happens during a complete stop. There are two phases. First, the reaction phase. This is the distance the car travels while the driver is reacting before they even touch the brake. And second, the braking phase. This is the distance the car travels while actually slowing down to a stop. The total stopping distance is the sum of these two distances. First, let's convert our initial speed from kilometers per hour to meters per second. To do this, we multiply by 1,000 meters per kilometer and divide by 3,600 seconds per hour. This gives us 26.39 meters per second. Now, let's calculate the reaction distance. During the reaction time, the car continues at constant speed, so we can use the simple formula. Distance equals velocity times time. Plugging in our values. 26.39 meters per second times 1.0 seconds gives us 26.39 meters traveled during the reaction phase. For the braking distance, we'll use the equation that relates velocity and acceleration to distance. Since our final velocity is 0, we can use v final squared equals v initial squared plus 2 times acceleration times distance. Rearranging this for distance, we get braking distance equals v initial squared divided by 2 times the magnitude of acceleration. Let's solve part of first, where the deceleration is 5.0 meters per second squared. Plugging in our initial velocity of 26.39 meters per second and acceleration of negative 5.0 meters per second squared, we get a braking distance of 69.68 meters. Adding this to our reaction distance gives us a total stopping distance of 96.07 meters. For part B, we use the same process, but with a deceleration of 7.0 meters per second squared. Using the same initial velocity, but now with acceleration of negative 7.0 meters per second squared, we get a braking distance of 49.77 meters. The total stopping distance in this case is 76.16 meters. Notice that with stronger braking, that is greater deceleration, we get a shorter stopping distance. The stopping distance at negative 7.0 meters per second squared is about 20 meters shorter than at negative 5.0 meters per second squared. This makes sense because stronger brakes can stop the car more quickly,